All right. Hello, everyone. Welcome back to Comp 3430 Operating Systems. Today, I want to spend just a little bit more time with IPC stuff. I want to spend just a little bit more time with that. And then what I want us to do is spend some time talking about threads. So we've got processes. We've spent a week with processes now. And processes are a mechanism for concurrency. We've got two different units of work, two different programs usually, that are running at the same time. So air quotes here, at the same time. They're running at the same time. Our textbook, it doesn't ever really say this. It doesn't ever really say this, but the kind of artificial constraint that the textbook is operating under is that there's one CPU on the system, one physical CPU. There are not many cores, there's not many processors, there's one CPU, and it's a shared resource across all of these units of work that we're doing. So when I do air quotes at the same time with processes, I mean, it's like there's multiple things that are making progress, but they're not literally physically running at the same time because there's only one CPU, or just doing that rapid switch and back and forth between them. Threads are another mechanism for concurrency that we're going to take a look at that kind of help us with some of the issues that we've got with processes and introduce some of their own brand new problems. We're going to be looking at threads in terms of, again, how do we use them? What does it mean to create a new thread? We're going to be looking at them from the perspective of synchronization, so using the same kinds of terminology that we were for processes. So when do we block? But we're going to be specifically now talking about things like how do I ensure that two threads that are executing concurrently don't make changes to the same thing at the same time. With processes, our discussion was a lot about like when does a process stop and when does it wait for things to happen? More like now there's data for you to work with. With threads, we're going to be looking at this as I never want two processes to be doing something to this thing at the same time. So how do we prevent that from happening? So by the end of today's lecture, what I am hoping that you are able to do is compare and contrast processes, threads, and applications. So we've got lots of stuff about processes. We'll start taking a look at threads, and then applications. As a reminder, this is a synonym for program. This is a synonym for that inert file that's on disk. Write code that uses library calls to create and manage threads. We're going to see, and I've intentionally chosen this word, library calls. We're going to see that threads are kind of invoked at the OS level on Linux using a system call, but we're not going to call that system call ourselves. We are not going to call that. We're going to be using the pthreads library to do all this work for us. Pthreads is a way to do threads. P in pthreads stands for POSIX. POSIX is an acronym for I don't know what. I have no idea what POSIX stands for. POSIX, POSIX. Pthreads is POSIX threads. We're going to be using a library to work with POSIX threads, and that's kind of like the de facto standard on Linux. Pthreads are available on macOS. Pthreads are not available on Windows. This is not something that you can do on Windows. You can do threaded processes on Windows, but it's not pthreads that you're using. The ideas that we're talking about here kind of translate between what you use on Windows for threading and what we're using on Linux and Mac OS for threading. The last thing that I want to be able to do, and this is beginning, this is start to identify critical sections requiring mutually exclusive access to a piece of code that would be running concurrently using threads or processes. There's not so much to do here with processes. There's not so much to do here with processes because when we fork a process, they're two completely different things. They're completely separate from each other. The shared resources that processes have is like it's pipes, read and write with pipes. The shared critical sections, shared pieces of code that processes have are signals, so like interacting with processes that way. With threads, this becomes a bigger issue. and we'll take a look at this. So I want to take the time to talk about this. I want to spend just a little bit more time talking about the Octopipe solution specifically. And I kind of want to talk about this. Okay, so there was a really good question asked yesterday. About, like, you've got all these right ends that are still open, and when we're duplicating it was a really good question that you asked yesterday. When we duplicate the process, like, aren't all those right ends open in the duplicate process? And the answer is yes, they are. And first I want to apologize. I kind of gave you like a brush off answer, and I don't really want to like leaving it that way. I don't like leaving it that way. So sorry that I did that. I was kind of feeling like, I got to get to the end of the class. We got to get to this next stuff. We really, really got to get to this next stuff. But a better answer in the time would have been like, I'll find out and I'll talk to you about it later. And that's what I'm doing right now. I'm trying to fix that. So sorry that I gave you a non-answer, and I didn't mean to brush you off, but let's talk about it now. So the way that I want to do this is in light of some feedback that I got from another student that was, can you please draw some diagrams to show us what's actually happening here? And I'd like to do that. So let's take a look at some diagrams here. This on the left side is my like Octopipe pseudocode. I'm not going to put that code up again. I've written down enough here to represent the state of what's going on with this Octopipe, the way that I did it. Got a loop that is iterating over the arguments that have been passed to this program. We're calling pipe, we're calling fork, and then in the parent and the child, we're doing two different things. I don't really care right now about which is the read end and which is the write end, so I'm just going to write R and W to represent the read and the write end. I'm going to write dup2 R and out to say standard output file no instead of writing standard output file no, but the broad strokes are here of what this diagram looks like. When our process initially starts, so we run Octopipe on the command line, the operating system is going to create a PCB for Octopipe. Part of the PCB for Octopipe is an open file table here. And this is the result of the shell doing that whole fork exec process. The shell is doing fork, the shell is doing exec. And what exec is being passed by the shell is Octopipe for our program. The PID it's not 1, but I'm just going to start with 1 because that's a good number to start counting at. The initial state of Octopipe is that the open file table has 3 handles here, and I've numbered them going all the way up to 5 ... But each of these entries is going to represent one thing. I've also got another thing in the OS side, which is this thing that I've marked as global. The operating system has process control blocks for processes, but those process control blocks can refer to other things in the operating system space. Global here in the operating system space is that Octopipe, when it's initially launched, its standard input is the keyboard. It's the same standard input that is the keyboard that our shell had. The standard output and the standard error are the monitor or the terminal window. So this is my very bad drawing of a terminal window here. These are references to those global things. The shell and Octopipe both share these things right now. Let's start stepping through this. So the very first thing that Octopipe does is it calls pipe. And when it calls pipe, it's going to create 2 new entries in the open file table. Yeah, we've got an array and stuff in our own code, but I'm just going to be talking about the open file table stuff here. So in the open file table, calling pipe is going to create a new entry for read, and it's going to create a new entry for write. The read and the write entries for this pipe are going to correspond to something that's in the global space, in the global part of what the operating system is keeping track of. And I'm going to call this just Q sub 1 for now. This is Q1. This is the first pipe that's being made between two processes. The read end of this pipe corresponds to the part of the queue that we'd be dequeuing things from, so taking stuff off the front. The right end corresponds to the part where we're enqueuing stuff. So I'll draw an arrow over to the other side here of this queue. We write stuff to one end, we read stuff off the other end. After we call pipe, this is our state. Once we call fork, now we're asking the operating system, please duplicate the PCB that I've got in the state that it's in right now. So I'm going to duplicate this PCB. Copy and then paste. This is going to be modified to be process ID 2. We've got a child and we've got a parent. The standard in, standard out, and standard error, just after we've called fork, all refer back up to the same places that they did in the parent. They all refer to the same global resources. So standard input in our child process still refers to this keyboard. Standard output and standard error both refer to the terminal. And the read and the write ends of the pipe still refer to this global queue object. So the read refers to the front, the write refers to the back. Between these two processes now, we're doing different things. In the parent, we're closing the read end, Closing the read end here is deleting this entry from the open file table for the parent process. But it leaves the queue there, and it leaves the read open end in the PCB for the child process. And then the parent kind of goes on and does other stuff. The child process closes the write end. I'm going to erase some of these arrows now. Closes the write end. And so now we've got just two things that are pointing at this queue. The child process duplicates. It does dup2. It says, I want to put the read end of this pipe and I want to replace the standard output in my open file table. So that's basically saying, I'd like to take this entry here and I'd like to delete it. And I'm going to copy the read end of this pipe. So input here is no longer referring to the keyboard, but instead it's referring to the read end of this pipe. So now we've got two things, two read ends that are pointing to that pipe. One that's pointing to the right side of it, this queue here. The child process calls exec. And what that does now is basically say, like, I would like you to take the code that's in this program file, and I'd just like you to replace my code section. So think back to, did you talk about address spaces in Comp 2280? A little bit, like code stack heap at the bottom? Okay, yeah. So the exec call is basically saying, I'd like you to take my code section and overwrite it with the code section that's in this file that I'm passing to you. So the open file table in the PCB, all of that stays the same, so that when we're calling read on standard input in this process, after we've done exec, it's still going to be reading from this queue. That's still not what your question was. I'm going to get to it. That's still not what your question was. The question is, now I'm going to do this again. I'm going to start the loop all over again. The loop is going to start at the top. It's going to call pipe again. And what that's going to do is the child process has gone off. It's doing its own thing. It's been replaced by catch. It's probably not going to call pipe again, so we don't really have to worry too much about its open file table anymore. The parent is going to start calling pipe again, and it is going to say, I would like to have a new pipe, please, and it's going to have entries in the open file table R and W. R and W are going to refer to a new pipe, a new queue. So I'm going to add a new queue down here, Q2. The read end is going to refer to, I'm going to change my color here so I'm not just making arrows that are the same color going all over the place. I'll make these ones blue. The read end is referring to this queue, the part where we're going to be able to dequeue stuff from. The write end is going to refer to the other side of it where we're going to add stuff to. Then we call fork, and fork is duplicating our PCB. So I'm going to copy and paste PID1 again. I'm going to scroll down a little bit here. I'm going to paste. I'm not going to draw the arrows back to the keyboard, and I'm not going to draw the arrows. I want to try to keep this a little bit more clean. PID is now 3. We still have standard input, standard output, standard error. These all still refer at this moment right now to the shared global resources. The right end of the pipe that we had here, I'm going to switch back to black. The right end of the pipe is still referring back up here. And this is your question. This is your question, right? Yeah. So the right end is still referring back up there. The read and the write ends are referring to Q2. And in the child process, we close the write end in the child process. So I'm going to cross the right end off here. This one. But we've got that duplicated write end from the parent process. We have that duplicated write end from the parent process still. We don't close the read end. And then the parent process up here, it closes the read end of this pipe because it never wants to read from that queue. It never wants to read from that queue. I'm going to stop duplicating processes here because we're in a state that's good enough to kind of demonstrate what's happening, why this still works, why it coincidentally still works, why it coincidentally still works. We've got 2 write ends open in the main process, the parent process. We have no write ends open in the first child that we launched. We have 1 write end open in the third one that we launched. The read end that the child refers to, the first child refers to, is the read end of this one. And the one that the second one is referring to is mostly just in Q2, but it's also referring to Q1 here. In the way that this was working, after we'd finished piping and then forking all those processes, after the parent process is finished, then we've got a loop, another loop after that. That's the parent only, that's doing read on standard input. And then eventually there's a loop that closes the pipes. And this is closing all the write ends of the pipes that the parent process still knows about. So we read standard input a bunch of times, we write standard input, we write what we read on standard input a bunch of times to those pipes. Those pipes print out to their standard output. After we get 0 from read, then we go to this loop and we start closing these pipes. So the parent process starts closing all the right ends of the pipes that it knows about. So it closes this one and it closes this one. I'm going to erase some of the lines here. So we're closing all of these arrows here. All of these arrows have been erased. This is Q2. We closed all of those right ends to the pipes. And what we've got right now is that the Q that process 2 was reading from, Q1, still has a writer open to it. The Q that Q2 is writing to here, process 3, sorry, I forgot to erase this one, doesn't have any writers left on it. We closed that one, so it doesn't have any writers left. So the only thing that's sitting around on Q2 here is this one reader. When the close happens, that means that the reader is going to get 0 back. It will get 0 back, and then it's going to exit its loop, and then it's going to exit. So programs like Catch, they've got a while read standard input loop. They get 0, and then eventually they exit. Part of the exit process of a process, part of the shutdown part of a process, the operating system says you called the exit system call. Exit basically says you can feel free to delete my PCB and release all my resources. So what happens then is the read end gets closed and the write end gets closed for this process. When the write end for this process gets closed, that means that its writer back up here is gone, and now there's no writers left on Q1. There's no writers left on this pipe. So that means that this process's read gets 0 back, and it's free to terminate because there's nothing else left for it to write to or to read from. So the read end gets closed, and there's no more write end left. So the order of operations here in terms of the processes getting torn down, after the close happens, and then later we've got this loop on wait. After we tear them down, we're waiting on null. The order of operations here is basically that the last process that's launched terminates, and then it kind of cascades backwards because we're slowly closing all of the pipes as those processes are exiting. If we had done the other option, which was like, let's write a loop in each child process. So here, not just close the W that was created for the pipe that's for me, but close all the other Ws. When we get to this point, and when we get to this point, then it would be kind of like, if we don't know what the order of actual shutdown is going to be, but here, because we've got all those right ends open, and the last one that we created doesn't, it's the last one that has a right end open, it just cascades the rest of them up. All right, so does that answer your question? Okay, good, thank you. Yeah. Yes, yes. No, you've got the right idea. So in this state, we had a queue, a pipe that has only one writer to it, which was the main process. And then once that was closed, this one is still, it may be blocked on read, but if it's blocked on read, once that pipe closes, once the write end is closed, the read will then return and say there's nothing left. So you can proceed. And then the programs that we're using, all of them, the programs that we were testing with, all of them were just like, okay, there's nothing left on input, so I can also just exit. Yeah, yeah. Whatever ends are left over, once the exit system call is made, once you return from main, then the operating system will just go through and close up everything and clean up after you. Yeah. So you don't necessarily have to explicitly call it, it'll just happen because your process has exited. Otherwise, it would be a resource leak in the operating system, and that would be a bug in the OS. Yeah. Standard in. So I did actually copy. Did I? The arrows are a mess here. I'm sorry.
No, I'm talking about right there, the default is in 2.
Oh, yes. Thank you. That should say in.
Should be in.
Yeah. Yeah. Okay. Yeah. Yes.
When one of them is so you know when to close the end. Like it's a very good question, but I don't know when it will implicitly call to close the end.
It implicitly calls to close any end of the pipe when the program exits. In exec, so like when we call exec, it's going to be replaced with the program code for something like cat or head or tail, something like that. That's actually not going to close anything because it doesn't know anything about the pipes. But eventually, so in something like cat.c, so we've got this program cat.c, it has while read std in, it's got something like this. And then eventually it's going to call exit, or it's going to return. And this is in the main function. When either of these are called, we leave the main function or we call exit. At that point, the operating system is going to go through the process control block for this process and start to close up resources like this. So cat would never call close on standard input or standard output or any of these pipes. But when it calls exit or when it leaves the main method, the operating system is going to tape over and just clean up on its behalf. In a separate program. So this is in the program that we're passing to exec. The first argument we pass to exec is the name of the file that we want to launch. And this is just like the compiled source code for something like cat.c. So if we were to look this up, and we can look up the source code for cat and see what it looks like. It has a main function, it's got a loop, it's got an exit. Yeah. So that's a good question. The question is, if all of the programs share standard input, I stopped drawing the arrows up here, but all of them are referring back. They're referring initially to this stdin. That's a good question. And what you might have noticed one time, this is a very small event that happened in our class, but one time when I was writing a program, I had to press enter twice. And the way that that's working is that one program gets to read, and then the next program gets to read, and then the next program gets to read, and then it goes back to the first one. And it kind of depends on which one calls read first. So there is one standard input per shell. I'm going to say it that way. There's one standard input per shell. I'm going to pop over here for a second. I've got two shells here. There are two different standard inputs, right? There's one on the left and there's one on the right. So this is left, this is right. If I launch a process from this side and it launches its own process, then they both share the same standard input that is this terminal or this side of my shell. If I launch it over here, they share the same standard input. But it's a common resource, and so they can all each call read on it if they want to, but they're going to get back different results each time. Yeah. Okay, good. Okay, we're good? Good, excellent. Again, I'm sorry. I shouldn't just like honestly, I shouldn't just freak out and be like, no, I can't answer that question. I shouldn't freak out and be like, I don't know the answer to that question right now. I should tell you, I don't know the answer to that question, or I will answer it later. And I'm going to make a better effort to do that, okay? I'm going to make a better effort to do that going forward. All right, so let's leave pipes and fork and exec and dupe 2 behind in class. You can keep working on this on your assignment, but we're going to leave this behind for now in class, and we're going to move on to the next topic. Let's start talking about threads. So processes are described as, so this is kind of a de facto or like just well-known concept out there. Processes are described as heavyweight. They're big things. They're big things that cost a lot when you create them. So when you call things like fork, it takes a lot of effort on the part of the OS to do a duplication of all the stuff related to a process. Another term that we use to describe this is that this is coarse-grained concurrency. I want to do a term check here. Do we all know what the difference is between coarse-grained and fine-grained, just in general, not even with relation? If you don't know, quickly stick your hand up. Okay, coarse-grained, so like literally think of sand. Literally think of sand. You're at the beach right now, and there's one part of the beach that's got lots of big pebbles, and then there's another part of the beach that has really, really nice feeling sand on your fingers. Coarse-grained is the big pebbles, and fine-grained is like that sand that feels really, really nice in your fingers. Processes are coarse-grained concurrency, and we think of them as coarse-grained concurrency because when we do this duplication process, we create a new process, it gets everything of its own. Everything is of its own. We can do communication between processes, but it's kind of like we have to make a big effort to do communication between processes, pipes and signals. We can work with files. We can tell processes that they should be working with specific files. We can pass information to processes by changing a variable's value just before we fork. But ultimately, we're getting these big objects that are all self-contained and separate from each other. This is coarse-grained concurrency. Threads are lightweight concurrency. So again, air quotes here, they are lightweight concurrency, but they are fine-grained concurrency. A thread is a concurrency mechanism, and the relationship, we'll talk about this again, I'll bring this up again, the relationship between a thread and a process is that a process contains or has within it one or more threads of execution. So we've got this process, and so far we've been thinking about it as there's a process. That's it. It just has an instruction pointer, it has a stack pointer, and we've just got like control flow, and it happens. On top of processes, we now have to start thinking about this abstraction of threads of execution within a process. A process has a main thread of execution that gets created when it starts, coarse-grained concurrency. We can add more threads of execution to one single process without making a new process. Let's do a quiz. So this quiz is kind of like a pre-assessment of threads. So I'm wanting to see approximately how much you've gotten from the textbook chapters on threads for this week. This is also no stakes. You know, if you answer wrong, it's not that big of a deal. It's partly for me to get a sense of how much I should be stopping and kind of going into things. I'd really love to know how they come up with these icons, avatars. Like, is it just like a, do they just have an artist that makes them, or is it like Mr. Potato Head where they're grabbing different things and putting it on. I'll give you 2 more seconds to join. All right. Good. This is kind of like, I just use these words, heavyweight and lightweight, fine-grained and coarse-grained concurrency. Threads, programs. Okay, let's talk about programs for a second. You write your C program, you write your LC3 assembly language program, and then you compile it, and then there's binary code on the disk. A thread is running the same binary code that a process is running. It's the same thing. It can't make instructions go faster because it's in a thread versus a process. So in that sense, in that specific sense, threads are not any faster than processes because it's just code. It's just code all the way down. I'm delighted that one person is all about cross-stitching and less interested in formalizing activities, but yes, address space is shared among threads. So in 2280, you talked about this idea of address space layout. We've got code, stack, heap. Code, heap, stack. Code, heap, stack. We've got code, heap, stack. Stack grows up, heap grows down. When we were creating processes, and let me just quickly pop over here. When we were creating these processes, part of this PCB for each of these processes is an address space. Part of this is an address space. And each time we're duplicating this PCB, we're kind of also duplicating that address space. The changes that this process makes to its address space, making changes to variables, doesn't affect this address space. When we talk about threads, our address space here is going to be more like, I've got an address space that's got a code, heap, and stack with PID 10, I don't know, something like that. We've got PID 10. With a thread, what we're actually going to have is like stack 1, stack 2, and then stack n. And we're going to have separate stack pointers and separate instruction pointers for each thread of execution. But they're all going to share the same heap. They're all going to share physically the same code segment. So the main difference between processes and threads is that the address space of a group of threads is shared. They're all within the same address space. Good. Power Oryx. Oh, let's do this and then I'll come to you. Yeah. Okay. So I'm going to come to you in a second. Yes, we can definitely communicate among threads. This could be a correct answer. I will say, I'll give you some credit. I'll give you some credit if you answered this one, that could be a correct answer. Threads could communicate through files. With processes, we absolutely needed some kind of external mechanism to communicate between things. We had to use a library, we had to use system calls to be able to do things like pipe and signal. We had to have that. But with threads, well, threads all just share the same address space. They just share the exact same address space. So in my threads, if I've got some file scope variable that's called something like x is equal to whatever, x is equal to 0, any of these threads of execution can just make a change to that variable, and then they can communicate with each other. We can have an array of characters, a string, and we can just put stuff in that array of characters, that string. We could have a queue, and we could just enqueue to the queue. I'm going to come to you in just a second. I'm sorry that I didn't get your question last time. What was your question? Yeah.
Like all of them run concurrently, or some of them may be running order. And I also wonder what would be any difference between the process and the function?
So that's a good question. If we have multiple threads within a process, do they run concurrently? That was your first question, right? So yes, they can run concurrently. They can run, again, at the same time. So each thread of execution within this address space will get a turn on the CPU. It will get a chance to run for a little bit. If there are many physical CPUs, they could literally be running at the same time. So thread 1 would be on core 1, thread 2 would be on core 2, thread 3 would be on core 3. Are threads like functions? Was that what your next question was?
Running in order, like person in order to be scheduled after that.
So we actually can't make that prediction in the same way that we couldn't decide whether or not which of the parent or child would get to run first. So I think your question, and please correct me if I'm mistaking your question, I think your question is, do we have to run one and then the next one and then the next one? When we start threads, it's kind of the same as starting processes. So we would call the thing to create a thread in a loop in the same way that we call fork in a loop. But once they're created, it's up to the operating system to decide which one gets to run at any given time. And the operating system might make somewhat arbitrary looking decisions about which thread gets to go next within a process. But it's the OS's responsibility to make that decision. Okay. So in terms of like running things faster, I was really explicitly meaning like, does a thread make instructions go faster? That was more what I was getting at. And maybe the answer wasn't clear, but in that specific sense, a thread is not going to execute instructions any faster. Yeah. Okay. Yeah. Related threads share the same heap. Threads that are executing within a process share the same heap, but not the same stack, no. So I guess when I drew this line here, I'm kind of trying to draw this to a place that's neither the heap nor the stack, because I'm trying to say, and maybe I'll say it right now, I'm trying to say that that's a file scope variable. So it kind of lives outside the heap. It's not part of the heap. It's also not part of the stack because it's not in a function. It's just kind of like, it's the global file scope variable. Yeah, yeah. But then each thread is going to get its own stack. And then the variables that you declare within a function, for example, these are thread local. They're attached just to that thread's stack. Yeah. Okay, good. Yeah. Does each type of thread? Yes. Every process was going to get its own address space, and that's kind of part of that fork process. It's duplicating the address space. I'm going to put air quotes on that again. It's duplicating the address space. We'll see later that it's not actually duplicating the address space, but yes, yeah. So is that why the virtual address of those two variables across those two processes, when we printed it out, is that why it was the same? Yes, that's why, yeah. Okay, all right. All right. So, what is a critical section? The memory that threads share, it's definitely related to the idea of what a critical section is, but memory that's shared between threads in and of itself is not a critical section. A block of code that threads share, again, it's related, but it's not in and of itself a critical section. A block of code that threads share, threads all share the same code section. They all share the same code section, but they each independently have their own instruction pointer. They each independently have their own stack. And a block of code that must be executed concurrently, this is kind of a red herring. Red herring is just like an English idiom that says it's something that maybe looks like it's correct, but it actually has nothing to do with what we're talking about. A block of code that must be executed concurrently, we could maybe run this with threads, but it's not necessarily anything to do with critical sections. A block of code that contains a race condition. Race condition here is basically we've got some piece of shared memory. So that's that first red block there, the memory that threads share. We've got some piece of memory that threads share. We've got a block of code that threads share. A race condition here is a block of code that threads share is trying to make changes to memory that threads share. So they're all separately trying to make changes to one common location. This is a critical section, something that contains a race condition where one thread making changes to memory may not be fully finished before another thread starts executing. All right. Oh no. Okay. Okay. Let's start with this one. Addition is not atomic. Addition is atomic. So think back to 2280. I'm gonna say that a lot. Think back to 2280. Addition is atomic in the sense that addition is something that is done like on that ALU. You get inputs and then it gives you some output, and this is just one cycle. It's a single cycle operation. Instructions are not atomic, and statements are not atomic. These ones look pretty similar to each other. Fetching instructions is not atomic, so this is like reading from memory, putting that instruction on the decode unit, and then like going through that whole process of running the control unit and starting to execute the instruction. fetching an instruction and then executing an instruction here, these may take multiple cycles. They might take multiple cycles of the CPU, but they are atomic in and of themselves. The add instruction is an atomic operation. It either completely finishes or it doesn't finish yet. The load instruction is an atomic operation. It either completely finishes or it doesn't finish yet. The branch instruction is an atomic operation. It either finishes completely or does not finish yet. It doesn't halfway finish and then get interrupted. Statements are not atomic. Statements, when I'm talking about statements here, I'm referring to like high-level language, C. Plus plus is a statement. That is not an atomic operation. It will compile down. We take the statement and we compile it down to assembly. It's going to be a bunch of instructions. So one line of code may have a bunch of instructions, and all of those instructions independently, they are atomic, but in sequence, they are not atomic. We can interrupt kind of in the middle of the execution of those instructions. So statements are not atomic. Instructions are atomic. Instructions themselves are atomic, but statements in a high-level language are not atomic. This is just like completely switched here. Just completely switched. Okay, here's the last question. Good, good, good. So locks and atomic operations, this is an okay answer. Atomic operations are something that we are going to use to build synchronization tools, but an atomic operation in and of itself is not a synchronization tool. Threads and processes are concurrency mechanisms, but not synchronization tools. They use synchronization tools. So like when we call read, it blocks. When we use the synchronization tools for threads, they will be within a thread and not a synchronization tool in and of itself. And locks and locks and locks and locks and locks. I'm glad that some people picked that. Yeah. Okay, any questions about that? Good. Okay, let's see. Green deer. Okay, good. Bolt hen. The names that it generates have nothing to do with the avatars. They're completely just like Groovy Dove. Groovy Dove is a moose. Okay, congratulations, Groovy Dove. Well done. Yeah, yeah. Okay, so switch back to my slides here. I want to take the time to take a program that uses processes and change it to use threads. So I want to use something that we've seen before with processes and just modify it to use threads instead of processes, just to get a sense of what this looks like as we're going through the process, of migrating from processes to threads. So this is an example that I've posted up on the course webpage as a starting point. This is hello.c. This is something that we had looked at earlier in the term. We're talking about getchar here and how it blocks. We're calling fork. We're doing some printfs. We're just checking to see which branch we're in this code section. This is slightly modified from that. I've changed a couple things, but it's otherwise exactly the same as the hello.c that I've given you before. If you want to follow along with what I'm doing here, please take the time to download this, and then we can kind of work together on it. So my goal here right now is mainly to see two things. One is, how do we start a thread? How do we start a thread? And 2 is, what about this whole shared address space thing? So what does that actually look like in the context of a program that looks like this? I'm going to remind you of what the output of this program is to get started. So we get this character input, we fork, and then we print out different things in the child and parent process. The child process tries to change that value. We wait for the child to finish, and then we're demonstrating that the address spaces, they're different. So the change that's happening in the parent, the change that's happening in the child process doesn't affect what's going on in the parent process after it's been done. So I'll make that, I'll run hello, I'll press B here, and then I'll enter D, W, that's very different from B. And after we finish running, the parent still has B. The address space that we've got in the child has not had any effect. The changes that we've made to the address space in the child hasn't had any effect in the address space in the parent. Okay, good. We're using pthreads here. The library call that we need to use to launch a new thread within a process is called pthread create. I'm going to take a look at the manual page for pthread create. Pthread create kind of looks like what our signal registration code looked like, in that pthread create takes a function pointer. Fork, the code, the system call that we're making to duplicate our PCB, it doesn't take any inputs. It gives us something back, which is the process ID of the child, but we're not saying, hey, when you start executing over here. It's just like it continues executing from the same spot in both of the processes. With pthread create, what we're doing is we are passing it some stuff, a pthread attributes, and then a function pointer that we want it to start running in, and then some arguments that we want to pass to that. What we're saying here is when this thread starts, I want it to start in this function. I want it to start executing in this function. When the operating system says, okay, it's time to start this thread of execution, it's going to start running in this function. It's not going to start running in the main code that we've got. If we want to pass arguments to it, we can pass arguments to it in this void pointer. So this is extra stuff that gets passed to the function that starts executing. I want to quickly look through this manual page too. The manual page for pthreads, the manual pages for pthreads in general are very good. Whether you're looking at them in the terminal here or if you're looking at them in your web browser, it doesn't really matter where you look at them. But the manual pages are really good, mainly because as I scroll down here, it's got examples. It has examples. Examples they're good. I like examples. I like examples. I like examples because it shows us what it should look like when we run it. And then it shows us the source code that's used to generate that output. Great, good. I like examples in manual pages. The other place that I want to look at the manual page for this, I'm going to go way, way down here. Way, way down here. It's a pretty big example. Is the see also section in the manual page. When you're looking at a manual page for a function, you have interest in this specific function, there's almost always this see also part that's at the bottom that gives you kind of like links to other manual pages that are going to be important for you later. This one right here, pthread join, we've got fork and then we've got wait. We're going to have pthread create and we're going to have pthread join. So pthread join is kind of like wait for these threads of execution to finish executing. But the other one that I really like to look at here is this section 7. So when we were talking about signals, section 7 for signal was like a long description of signals. Section 7 for pthreads, man 7 pthreads, is a very good overall description of what pthreads are. A single process can contain multiple threads, all of which are executing the same program. I like this. I like that this stuff is in here. Okay, so let's get back to the task that we're looking at right now. So I'm going to say man pthread create again. And what I am actually going to do is I want to start bringing this stuff in. So I'm going to zoom out. The first thing that I've got to do is include pthread.h. So let's do that. The other thing that it says to do here is compile and link with -pthread. I'm going to show you that I've made this change already and that you are going to need to make this change yourself when you are modifying your own makefiles. I've done this just like slightly differently than what they're showing here. The change that I made to this was to add this ld_libs variable and say that it's equal to -l pthread. So this is linked to the pthreads library when you're compiling this code. The rest of the stuff I haven't really changed. So we're still using the default rules for building our C program. So I'm going to quit my makefile and I'm going to go back to the manual page for pthread create. Pthread create here says I want to take a thread pointer, a pointer to thread attributes for the thread, the function that I want to call to start, and then arguments that I want to pass to this. I'm going to start by commenting out this line where we did this duplication originally, where we were calling fork originally. I'm going to add to this pthread create. For now, I'm going to pass null to thread. I'm going to pass null to attributes. And I'm going to start having to think about what function it is that I want to actually have invoked by this thread. So null, null, something, and then null. I don't want to pass any arguments to this right now. The something here, I'm going to need to create a new function. The function signature here is that it must return a void pointer. So that's this right here. It must return a void pointer. It has to have a name, and then it has to accept as an argument a void pointer. So I want to put into pthread create here a reference to that. This is the name of the function that I want you to invoke when you start running this thread. With fork, we're saying make a new process, duplicate my PCB, and start running both processes from the same point. After assigning this value to child, just keep them going. Pthread create says, I would like to have a new thread of execution scheduled with this function. Started at some point, please, but I don't know when it's going to start. Kind of in the same way that fork is, I don't know when my child process is going to start. This is, I don't know when my thread is going to start, but I'd like it to start executing eventually, please. In the function, what I want to have going on, what I want to do is the stuff that I was doing in the child process. So all of this in the child process, enter a different char, c equals get char. This is the stuff that I want to do in my thread of execution now. So what I'm going to do is I'm going to copy and paste this. I'm actually going to just delete it. So X is to cut. And I'm going to paste it here into my thread. Here's a small aside. Here's a really small aside. I'm going to quit Vim for a second. One of the common things I see with students submitting work, and then another common thing I see with students losing points on code quality is like really weird indentation issues, like switching between tabs and spaces, especially when you don't notice that it's happening because your editor is helpfully just like, no, they're the same. They're approximately the same, so I don't really care. They're gonna look the same. In your editor, I'm a spaces person. I don't care for tabs. I don't like tabs. I prefer spaces. My editor is configured to make sure that I have 4 spaces. That's the correct number of spaces. We can have an argument about this if you really want to, but 4 is the right number of spaces. There's a code formatter for C programs called Clang format. Clang format will take your program .c and it will format it and print it out. I don't use Clang format. You can tell because it's defaulting to 2 spaces instead of 4, and 2 is the wrong number of spaces. But if you want to use Clang format, you can do something like hello formatted.c. There's an option to do inline formatting. I think it's -i. I think it's -i, but you should check the manual page for Clang format. It's just a code formatter, reads in your source code, formats it correctly, spits it back out again so that you don't have to do this yourself. So I'm going to go back to hello.c here. My thread is going to start executing in this function. C is now like in the main function and in the thread. I want C to be a file scope variable. I want it to be shared by both threads of execution that are operating in my process. So I'm going to go up here. I'm going to say char C, and I'm going to delete char C in here. I don't want this to be shadowed in the main function. Shadowing, shadowing, shadowing. I don't want to shadow 2150. You beat that to death. You beat shadowing to death. Does anybody actually remember the differences between method shadowing and virtual inheritance C++? Do you remember? Does anyone remember? Okay, so I'll put that on the test, right? Yeah, okay, no. Okay, so I want to have this as a file scope variable. I don't want to redeclare it in my main function. I want the changes in the main function to have effect everywhere in my address space, so I'm going to put this variable up here. I'm going to add static to this. Static in C, remember, or hey, this is new, static in C means like file scope, file private. It's private to this file. You can't use it in other files that you're including or using. I want this to be private to this file. In my main function, I still want to say getChar here. I still want to say getChar again. GetChar gets 1 character. When I press enter on my keyboard, I am submitting 2 characters. I only wanted to have 1 character in char C. GetChar again just removes that extra new line and discards it. I've launched this process, pthread create. I've got these lines that are printing out twice, once in the parent, once in the child. This doesn't happen anymore. Instead, what this is main thread. Main thread. And PID doesn't really get used anymore. It doesn't exist. So I'm going to delete child, and I'm going to delete PID. We could do like get PID instead. We want to get the process ID for this process, but I don't really care. Printf main thread, char is %c. My branch no longer makes sense here. So I'm going to delete all of that stuff. I'm going to indent it back. I'm going to say main thread. I'm going to delete this line that the child is something. And then I'm going to say man pthread join. Just like with processes, I want to block until the thread has finished executing. So I'm going to comment out wait. Pthread join here. Oh, it takes a pthread type t. So I'm going to have to create one of those. So let's do that. I'm going to add to the top of my main function here, pthread t thread. Pthread create took a pointer to that, so I'll pass the address of thread. Whoops. Pthread join here takes thread. Note that this just takes the variable. It's not the address of it. It's not a pointer to it. It just takes the variable. It will copy that struct. And then there's retval, void pointer, pointer retval. I don't care what the return value was. So null. And I'll say main thread again here. OK. And I'm going to delete that line. I'm going to add a comment here that says blocks wait for thread to finish. OK. Our API calls, they're obviously different API calls. One is fork and one is wait. The other is pthread create. The other is pthread join. But they're like synonyms for each other. One is create. One is block until the execution of this thing that I've created has finished. The paradigm of like fork and then have stuff run after this is slightly different because we're giving an address or a function pointer that says go up here and start executing. And we're able to make changes to the address space that we've got here. OK. So I'm going to make, and we've got like 3 minutes left. So I'm really going to hope that this works. I'm really, really going to hope that this works. OK. There's two things here, and I know how to fix those problems. The first one is unused parameter args. You are going to see this. You're going to see this. And that is related to W error. I've made warnings into errors, and unused parameters is either in extra or pedantic, but it's not in all, because all is not all. I'm going to say, I know that I'm not using this. And the way that I tell my compiler, I know that I'm not using this, and you can stop warning me about it, is to cast that value to void, and then don't do anything with it. This is like, it's no op, no operation. This is an instruction that doesn't do anything. It doesn't assign anything. It's just like, I'm going to use this variable. I know that I'm not using it, but the library that I'm using tells me that I have to have this in my body, in my function body. The other thing that we've got here is non-void function does not return a value. That's referring to my thread here, void star. It's expecting me to return a pointer to something. I'm not returning a pointer to anything. Return null. OK. Try that again. OK, good. Good, it compiles. Let's try this out. I'm going to hit hello. Right now, we are blocked on line 23. We're sitting here waiting for some input. I'll enter Z. That's the most creative letter I can come up with. I'm going to hit enter. When I hit enter, that's going to flush standard input, and it's going to send it to read that's in this process. We're calling read getChar. GetChar is calling read. It's asking for 1 byte. 1 byte will be stuffed into C. The new line character will still be there. So this is going to immediately get passed. We're not going to block there. The next line that's going to run is pthread create. And then we're going to say either printf the char is something, or we're going to start executing the thread. We cannot know. We can't deterministically know which is going to happen next. It's up to the OS, and it's kind of like what was going on with processes before. So main thread prints out first. in the parent process, the main thread of execution is blocked here on line 36. This process currently has 2 threads of execution. It is one process, but there are 2 threads of execution. We called pthread create one time, but that makes a new thread on top of the one that was there already. So we've got 2 threads of execution. The main thread of execution is blocked. It's waiting for the other thread of execution to finish. The other thread of execution is blocked. It's waiting for us to type some input. So one thread is blocked on line 14. The other thread is blocked on line 36. I'm going to enter something else here, and I'm going to hit enter. After we hit enter, the child thread, the second thread of execution unblocks and returns. Once we return from that function, the thread is over. The thread is finished. It has exited itself. Kind of like returning from main causes a process to exit. This is causing that thread of execution to exit. After that thread exits, the main thread of execution here unblocks. We've waited for it. It's finished. It's told us it's done, so we can proceed. And then what we're printing out here is that after I have run that thread, it's made changes to that file scope variable. Both of these threads of execution are running in the same address space. So the change that we made in that thread is present in the other process or the other thread of execution. All right, so I post this up. I'll post this up on the course webpage. Really quick summary here. The IPC making calls to pipe and fork and signal and stuff is using the open file table and the process control block, and it's making changes to that. Threads are an alternative concurrency mechanism, and we can now start using threads. We can create threads, and we can do some synchronization with them in the form of waiting for a thread of execution to finish. We'll get to the other parts next class. Thanks all for coming out, and I'll see you tomorrow. Bye, everybody.